We have two really nice speakers here, so if you are still waiting outside, please come in as soon as possible, because we already have here set up and ready to talk Aashish Clerk. So Aashish Clerk has been oscillating back and forward between the US-Canadian border many times, but is now finally settled in University of Chicago, where he's looking at many different things, mainly about dissipative methods, and it probably comes as no surprise that he'll be talking about that today. So his talk is titled Dissipative Approaches to Quantum Metrology, and we're really looking forward to your talk. So please take it away.
Great, thank you. Cool, so let me start by thanking the organizers. This has been a really fun conference. I think it's great to be exposed to such a wide variety of topics. It's also really nice to be at a conference where the dominant audience is students. And so in keeping with that, I will try to make this talk as user-friendly as possible, right, and as general. Apologies to the experts if I bore you. The session is quantum sensing and metrology, so I will talk about a topic related to sensing and metrology. I'm going to tell you about theoretical work in my group, where we're looking at ways of using dissipation as a resource for metrology. And specifically, the idea is to use dissipative collective interactions, if you want, dissipatively mediated spin-spin interactions, to make things that are normally very hard in quantum metrology a little bit easier. And there's like two stories I hope to tell you in a gentle way during this talk. The first is the idea that by using a particular kind of dissipation that is ubiquitous, a kind of superradiant decay process, that's a really, really nice way of preparing entangled states that are metrologically useful. So it's a uniquely powerful way of generating spin squeeze states, things you could actually do in an experiment as well. And then the second story, which is kind of a nice surprise as well, they're neat ways of using dissipation that allow you to, in an experiment, benefit from having an entangled state, even though in some ways your experiment is terrible. So you could be in a regime where you're measuring something, the measurement is completely limited by classical noise. You'd be like, quantum noise plays no role. There's a neat trick where dissipation changes the story, entanglement can still help you. Okay, so that's the goal. I only have 30 minutes, we'll see how far we get, and hopefully there's time for questions too. Let me start just by acknowledging the people who did the work. This is a line of research that's been going on in my group for a couple of years. I think the main player in the stories I'll tell you is a former postdoc, Martin Koppenhofer, who is now at one of the Fraunhofer Institutes. Peter, Kiro, and a new postdoc, Mikhail, are also playing a key role in this research. And what I will tell you is all theory, but it is inspired by some experiments. So all of this work is part of an ongoing experimental collaboration with Anya Blazinski-Jayic's group at UCSB. Okay, so I have certainly learned that this is a very broad audience and like people have very different backgrounds. This is a quantum metrology session. So let me start with like quantum metrology 101, right? And here is one of the most important and kind of ubiquitous tasks in quantum sensing. It's the idea of using a quantum state to estimate some classical parameter. So there's a magnetic field, a voltage, I don't know, the amplitude of a force you want to measure with high precision. What is the general approach? You have some sensor that's a quantum system. It starts in some quantum state. You're going to encode the parameter of interest. Maybe that's a magnetic field in the state. So you're going to evolve that state with a Hamiltonian that depends on that parameter. The state now depends on the parameter. You're going to measure it. And then you're going to process those measurement records or those measurement results and make the best possible estimate or guess as to what that parameter is. And the central question of quantum metrology is, what are the fundamental limits on how well I can do this? What sort of state should I use there? How do I have the right kind of entanglement that helps me? So just to make this concrete, and this is really the setting that I will be talking about this sort of general protocol throughout this talk, we could imagine that our sensor system is just a collection of two-level atoms, a collection of qubits, right? So here is my collection of spins. We're going to work in the limit where I could really think about this collection of spins as a collective angular momentum vector, right? I could sum up all of the Pauli matrices for each of those spins. I get some large S, angular momentum S, And now in terms of what am I trying to sense, again, the simplest thing you can imagine you're trying to sense is some small magnetic field. Okay, so what's the idea? I could represent the state of these spins as this giant vector, right? Let's just even think about it classically. So here is my generalized Bloch sphere. Maybe the parameter I'm trying to sense is a Z magnetic field. Okay, so I'm going to turn on that magnetic field. It's going to rotate my spins. So I start with the spins all pointing in the x direction. If you want, all the qubits are in superpositions of their Z eigenstates. Under this evolution, the vector is going to rotate a little bit. Okay, so that now is the state where we've encoded the parameter dependence. And then what would you measure to figure out what is that small phase? That's the thing you want to know about. Well, in this case here, I would look at the y component of this collective angular momentum. So the y component of the angular momentum would involve the number of spins, but it would also have that unknown parameter. Okay? So this is like a kind of cartoon version of like a Ramsey-style sensing protocol, ubiquitous in lots of experiments. What's the kind of fundamental question we could ask? What's the minimal estimation error you could get in this kind of protocol? Okay, and again, like summarizing a lot of beautiful work in like half a slide, there is a really well understood fundamental bound for how well you can do with this for this kind of estimation. And the minimum error you get really depends on whether you allow me to have entanglement or not in that initial state. So again, I'm thinking about using many, many qubits, many, many systems as my probe system. If I don't have any entanglement, the best I can do in terms of my estimation error of this parameter x is a scaling of 1 over the square root of n, where n is the number of qubits. And for the kind of sensing I just described to you, even that prefactor, it really is a 1. You can't do better than that. If you have entanglement in this initial state, and the right kind of entanglement, right, not just any old entangled state, then in principle, you can do dramatically better with the scaling. That 1 over square root of n becomes a 1 over n. This is referred to as Heisenberg limited scaling. Okay, and so one of the big questions is, can we actually realize this using tools that are available in the lab, right? What kind of entangled states do we need? How do we build them? How do we use them in a way that's robust against all of the kind of imperfections you might have to deal with in an experiment? Okay, so in the case that I'm interested in, where my system of interest will be a collection of spins, again, this cartoon again, and the parameter I'm trying to estimate is just this rotation of this collective angular momentum vector. There's an easy way of thinking about at least one kind of entangled state that's very, very useful. And so this is now getting at the idea of a spin squeeze state. So again, I want to sort of see how this angular momentum vector rotates a little bit. This is a very classical picture. If I want to make it more quantum, where is that arrow pointing? Well, the uncertainty principle tells me there's got to be a little bit of uncertainty, right, in exactly what those transverse components of angular momentum are. So I can imagine describing that with a, like a Wigner function, a Husimi function. There's this blob of uncertainty, and now if that blob has a width and I'm looking at a really, really small rotation, I won't be able to see it. So what's a really simple thing I could imagine doing at the level of PowerPoint? I could imagine just squishing that blob, right? Squeezing it. So I don't violate the uncertainty principle, right? I just move all of the uncertainty principle junk in this other direction here. So now if I rotate generate some Y polarization, it's going to be a lot easier to sort of sense that. Okay, so this squeezing in phase space that is very easy to understand at the level of a picture, that corresponds to entangling the spins in just the right way to begin with. Okay, and the metric for how well are you doing in terms of squeezing or getting this kind of right entangled state, it's this Ramsey parameter here. The crucial part is the numerator here. How much have you reduced the fluctuations in one of those transverse components of the angular momentum compared to what you would have had in a product state? And that directly then is going to determine how well is the, your estimation error scaling with the number of qubits. Okay, so that's a very, very quick and dirty and incomplete introduction to spin squeezing and some basics of quantum metrology. So the question now is, how do I get that nice state, right? I want the spins have to be entangled to give me this particular pattern, right, of uncertainty. So I have to make the spins interact, right? That's the simplest way you could think about getting this kind of state. And so the standard workhorse in this field for generating spin squeezing is this Hamiltonian here. So this is an all-to-all Ising interaction. This is often referred to as a one-axis twist Hamiltonian. The unitary dynamics generated by that Hamiltonian will generate this kind of spin squeeze state. So you can generate this if your spins are two-level atoms. You could have photon-mediated interactions that will generate this long-range all-to-all interaction. So the good thing is it's very easy to get this kind of dynamics in a lot of different systems. The bad thing is it will never let you reach the Heisenberg limited. So there's this fundamental limit in terms of how much entanglement can help you. This gets you better than just having a product state. It doesn't get you all the way. Okay, there's other more Baroque Hamiltonians we could talk about. That's not the focus of this talk. The focus of this talk is there's more to life than a Hamiltonian, right? What if we allow a more general kind of dynamics, right? So what if I allow non-unitary evolution? What if I allow dissipative evolution? I need to have my spins interact to get entanglement. What about having like dissipative interactions? Okay, so that's one thing I'm going to tell you. There is a clever way of coupling these spins to a structured environment. The environment will make them interact. That is going to generate entanglement in a way that has a lot of advantages over this standard way of doing things. Okay, what's another big problem if you're thinking of doing this in an experiment? Experiments are never perfect, right? And a big problem in experiments is typically you're not just limited by the fundamental noise in that quantum state. You're also limited by how do you make the final measurement? Is there additional noise in the readout? Okay, and so if I actually think about what is the error in estimating this parameter, phi, this rotation. So this is like a noise to signal ratio, right? So if I think about the noise, the stuff in the brackets here, this is the fundamental noise associated with the quantum state. This is the thing you could tackle by maybe doing some entanglement in that initial state. This here is now denoting all of the extra kind of classical junk associated with, look, you're not able to make perfect measurements, right? You don't realize the textbook ideal of a measurement that we would learn about in quantum mechanics. You typically end up adding a lot more noise than this projection noise limit. So then the question is there still a way to benefit from having entanglement in that state, even though this term here is naively much, much larger than this term here? So again, a long story made short. There's a beautiful set of ideas that have been developed by a number of different people, where if you just stick to unitary evolution, you can actually fight this detection noise by, in a way, using what people call a time reverse protocol. So you have some Hamiltonian here that generates entanglement. You evolve your spins under that. This is the unitary that encodes that rotation, puts the parameter dependence in. And then you evolve with the, let's call it the time reversed version of that Hamiltonian. Okay, so these protocols that people sometimes call twisting and untwisting, that actually gives you a way of trying to benefit from entanglement despite all of this kind of extra, added measurement noise. And again, the question I'm going to ask here, is there a dissipative version of doing one of these kind of time reverse protocols? Okay, and again, and I realize I'm already going much slower than I had expected. Just to give you motivation, and this was our motivation, right? In terms of the two-level systems or the qubits you might want to use, could you do something in the solid state, right? So could you use defects in a semiconductor as the qubits that you will use for sensing, right? So our motivation maybe came from using NV sensors in diamond, which are known to be very, very powerful sensors, let's say of small magnetic fields. The readout of an NV sensor in diamond that's based on spin-dependent fluorescence, this is what this is showing here. By these fundamental sort of metrics, it's kind of terrible, right? So if I look at my estimation error here, this is just the projection noise of just having a product state for your spins. This is quantifying how much extra noise is there because your readout isn't perfect. The best experiments have this number here being about 70. And for typical experiments, this is more like a factor of 1,000. So again, at first glance, you'd be like, why are people even trying to entangle these NV-center qubits for sensing? The readout is just not good enough. And again, what I want to tell you is not find a better way to do a readout. I want to give you a way where you can still use your kind of not so great readout, but play some tricks with the quantum state and the quantum dynamics such that entanglement can still help you. Okay, so that is the plan of the talk, like these kind of two stories I want to tell you. The first story is let's not be too demanding. We have this really, really terrible readout. If I could even just reach what we call the standard quantum limit, right, really reach a sensitivity that is on par with just the fundamental noise of a product state, that would already be kind of exciting, right? And I'll tell you a way of being able to do that. And in the second part of the talk, then we'll get greedy and we'll ask, let's still deal with a system where we have this insane amount of extra readout noise, but let's now try to do better than this scaling. Let's try to come closer to this Heisenberg limited scaling. Okay, and I'll just kind of sketch to you the ideas and what the resources you need to actually realize these two different goals. Okay, so the first thing is we're just going to try to reach this standard quantum limit scaling despite all of this enormous extra readout noise. The whole talk is about using dissipation to do this in some way. The dissipation we're going to use is kind of the simplest, almost the simplest dissipation you could think about. So I have qubits, I have two-level systems, I have a ground and an excited state. Typically, if I'm in the excited state, I will decay to the ground state, right? So we're going to use the physics of just that simple decay, but we're going to do something special with it. We're going to call it superradiant decay. I'm going to have interference in how all my different qubits actually decay. Okay, so I have a spin lowering operator for each of the n qubits in my ensemble that is my sensor. I can form this collective spin lowering operator, big S minus. So the dissipative dynamics I want is described by this Lindblad style master equation, where all of the dissipation corresponds to this S minus operator. And what does that mean physically? It really means that the qubits are decaying. If a qubit decays, then there's some excitation that goes out in the bath. I don't know which qubit actually decayed. And that interference is going to be crucial. How would you realize this? One way, in an experiment. Imagine all of my spins or atoms are sitting in a cavity. They're resonant with the cavity. The cavity is leaky. Photons can leak out. In this case, right, you would get a dissipative dynamics of this form. Okay, so this is superradiance. This is something that is, among the best studied effects in sort of quantum optics. There's an enormous amount of literature and beautiful experiments looking at superradiance. Normally what you look at is the interesting statistics of the photons leaving the cavity, right? And you get this kind of superradiant burst of photons coming out. We're going to ignore all of the photons leaving the cavity. The whole point here is this funny kind of decay is going to do something useful to our spins. And one way to think about that, let's just look at this Lindblad master equation expanded out. If I look at this term here, that almost looks like a Hamiltonian term, right? And it looks like a term where the spins are interacting with one another, right? Because again, this S plus and S minus, that's a sum over all of the individual single spin raising and lowering operators. So sitting in this dynamics is a kind of interaction between the spins. This is going to do something useful for us. Okay, and the cartoon picture of how this works is just incredibly simple to sort of explain. Okay, so again, it's always, we have this spin ensemble. There's a small rotation, right, that has the information we want, this angle phi. So what am I going to do after I put the information in this y component of my spin? I'm going to rotate it back so it's almost pointing in the North Pole. So the spins are almost all in their fully excited state, but there's a little bit of a y component that has the information I want. And now look, I have this simple decay dynamics. So I turn that on. What's going to happen? The arrow is going to fall down to the South Pole. That does not sound so great, right? But what is the nice thing here? If I didn't have any y component to begin with, there's no preferred way in terms of how the arrow goes from north to south, right? So all of those different pathways are equally probable. As soon as I start with some polarization there to begin with, I break that symmetry, right? So now the simple cartoon is, with that small polarization, right, there's a preferred trajectory for that collective angular momentum vector to follow. When it crosses the equator, it's going to be fully pointing in a direction that knows about that initial polarization that you started with. Okay, so one way of thinking about this, we're using the physics of superradiance to build a kind of spin amplifier. We're starting with this tiny amount of Y polarization. Phi is going to 0 at some really, really small phase we're interested in. This dynamics is going to make it large, right? So if I can stop the superradiant decay right at this point here, that small polarization is going to be amplified by something large. That something large is going to grow with the number of spins. It's going to grow as the square root of n. So as I have a bigger and bigger and bigger ensemble, this effect in principle gets better and better and better and better. Okay, and something crucial, I need the fancy superradiant decay operator. I don't want the spins to be able to decay from top to bottom by just kind of going through like the middle of the sphere, right? So this dynamics here conserves total spin angular momentum. That's crucial for this physics to work. Okay, so just to give you a sense of what this looks like, this is this gain parameter. So how big is Sy compared to that small value I started with as a function of time? This is for 120 spins. You see at that magic time, there's an enhancement here, right? In this case here, it's a little bit less than 5. But that really is growing, and that's what this is showing here, as the square root of n divided by 2. Okay, so long story made short, this is what the protocol looks like. I can come back to that. Let me even skip that just because time is growing short. Long story made short, here is our sensitivity in measuring a small phase. In units, that is the best you could do if you just had a product state and perfect measurement. This is starting in a case where the added noise of the measurement is kind of enormous. And so if you didn't do anything, even if you increase the number of spins, you're a factor of almost 70 above this quantum limit. As you increase the number of spins, this amplification effect gets bigger and bigger and bigger. You're able to reach this fundamental quantum limit. So in an experiment, of course, the dynamics is a lot more complicated than just that, right? This is the good dissipation, the thing I want. There's all sorts of terrible single spin dissipation that will also ruin things. That's something that we've also thought about. It turns out this physics is very, very robust against all of that unwanted dissipation. And if there's time, I'm happy to tell you more about that. So do I have 5 minutes? Is that? Okay, perfect. So in the last 5 minutes, we'll get greedier. So I've told you a way that you've got this system, your measurements are really terrible. You can still get the sensitivity of having perfect measurements and a product state, up to a factor of 2. Okay, the same scaling with n. Could we do better than that? Is there a way of actually coming closer to this Heisenberg limited scaling, where the sensitivity improves as 1 over n, not 1 over root n? Okay, and so I mentioned that there are these very clever ideas using the right kind of unitary evolution, where you first apply some interactions that generate entanglement, you encode the parameter of interest in your spins, and then you kind of apply the kind of reversed Hamiltonian. Okay, and this dynamics does something very nice that helps you fight that added noise. The thing that we've gotten excited about is there's a dissipative analog of that. So this idea here is, you can almost think of it as there's 2 steps where you have an interaction between the spins, and they're kind of time reversed. H goes to minus h. What's the dissipative version of that? Well, there's a dissipative evolution that will prepare an interesting entangled state, and it's going to be a version of that superradiance I told you about. You encode the information in between, and then there's the inverse, sort of like this minus h, dissipative operation that is basically going to amplify your information. Okay, and so this is going to be a dissipative way of trying to take advantage of having entanglement, even though you have a really, really inefficient readout. Okay, and so just quickly sketching the 2 steps of the dynamics that we need. So this is first, how do I prepare the interesting entangled state? I'm going to again use some dissipative dynamics that almost looks like our superradiant decay. So before I just had the dissipation being controlled by this collective spin lowering operator. So now this is some funny operator that's a linear combination of collective spin lowering and collective spin raising. Okay, so it turns out this is the dissipator I would get if my spins were sitting in a cavity and you were sending in strongly squeezed light. Okay, so this describes squeezed dissipation. There are ways of engineering this kind of dissipative dynamics that doesn't require any squeezed light. Right? Experimentalists typically don't like it when you say, I need 30 dB of squeezed light for this protocol to work. You don't need any squeezed light to sort of mimic this physics. So this dissipative dynamics, its steady state, will give you a Heisenberg limited squeeze state. Okay, and it has a lot of interesting, fun things that I don't have time to talk about. So this is the amount of squeezing as a function of this R parameter here. This line here that's like minus 20 dB for 200 spins, that's the Heisenberg limit. Okay, so R is big enough, you kind of reach that, that's great. If you go from 200 to 201 spins, the curve is now this dashed blue curve. So at really large values of R, you don't have any squeezing at all. So in terms of the funny physics of this dissipation, there's a regime where no matter how big the number of spins are, you're sensitive to the parity of the number of spins. Okay? If you don't care about that, you can avoid that just by working at a regime here where that effect doesn't show up. Okay, but the first thing is there's a way of dissipatively preparing a highly entangled state. And then what's the second part of the protocol, right, that's going to help us fight the measurement noise? We basically apply the same dissipator, but now we use it to do a kind of fancier version of that amplification I was telling you about. Okay, so now we've prepared our squeeze state. It's a little bit shifted from the North Pole. That's the signal of interest. So now again, I'm going to play this game of having this collective decay. As this thing falls down and tries to reach the South Pole, when it crosses the equator, I'm going to get an amplified signal. But now the initial state is squeezed, and now this superradiant decay, because there's that S plus there, it's also got some squeezing built into it. Okay, and the upshot of all of this is, and again, this is what the protocol looks like. The upshot of all of this is you can do better than the standard quantum limit, even if your detection noise is terrible. Okay, so these are showing results, again, measurement sensitivity in units of the standard quantum limit. This is a case where the detection noise is not terrible. The detection noise is on par with what the noise would be if you had a product state. And again, you would think that means I can't use entanglement to help me. And this is showing, you can just focus on this green curve here, as the number of spins increases, you're in this white region, not the gray region, you're doing better than the standard quantum limit. Okay, and then the last thing I will just flash up, there's always this hope that if you do things using dissipation, you're going to be protected against bad dissipation. So good dissipation beats bad dissipation in a way that maybe is more robust than having unitary dynamics compared to bad dissipation. For this protocol, that actually works out. If you try doing this kind of time reverse protocol just using a Hamiltonian interaction, that's what these red curves are. There's also an improvement, but it's actually much, much worse than this dissipative approach. Okay, so I'm pretty much at the end of my time, is that right? Yeah, okay, so then I will, there is a way of doing this in experiment. Anya is interested in trying to do this. Happy to tell you more about that. Let me just, I will put up the conclusions, but I will also take this opportunity just to take advantage of the fact that there are so many excellent students and maybe postdocs here. Not just me, but my colleagues at UChicago have lots of openings for students, postdocs, maybe even faculty, right, working in quantum science. So if you're at all interested in things that you heard about or other things my group does, please reach out to me. Okay, and with that, I will stop. I'll just leave the conclusions up here, and thank you.
thanks a lot for this very interesting talk. So questions from the audience?
Thank you very much for your beautiful overview. I have a question regarding the regime you want to operate.
Mm-hmm.
So I maybe missed, do you want to stay in a strong coupling regime? Do you want to be in a cell-enhanced decay regime? What is the ratio between the cell decay and the intrinsic decay? So could you kind of tell a little bit more?
Yeah, let me just go back to the very beginning because it's generic to all of this, right? So if you think about this cartoon, and so the idea is that all of your spins are coupled to a lossy bosonic mode. Here I've drawn it as a cavity mode. It could be a mechanical mode where you've engineered it to be lossy. You want to be in the regime where the decay rate of that mode is kind of the largest scale in the problem. So to get this kind of dissipative dynamics, I've kind of eliminated the bosonic degree of freedom completely, the cavity mode or the mechanical mode, to just get this simple dissipator. So again, I don't think I wrote it down here, but if I think of having a little g and I have a kappa there, kappa is actually much bigger than square root of ng. So it's the extreme bad cavity regime, if you want to use that kind of language. But we want the cavity to just act like a structured bath for the spins. Yeah.
There is a result out there, and you probably had it in your references, that describes how error correction can help with your problem. And then there's a condition whether the signal that you want to measure, your magnetic field, is in the linear span of these dissipation terms. And if it is, then that's bad luck for your error correction techniques. So you have dissipation in your problem. So from your angle, can you say something on that result? I mean, yeah.
Yeah, so I know that result well because I think my colleague Liang was actually one of the people that sort of did some of that work. So I think there's like a beautiful set of results that tell you what are the circumstances you need for error correction to help you in quantum sensing. This generic problem of using a Ramsey-style measurement to measure a small rotation, as soon as you have unwanted single spin dissipation, so I didn't even write those terms here because we all know what they are, right? Every spin has its own T2 and it has its own T1. That immediately puts you outside the regime where those techniques can help you, right? Now maybe there's some clever things to modify the problem, encode the signal in a different way, but a priori, like those error correction, those results tell you error correction will not help you here. Yeah.
And are you saying, but your techniques apply to that regime, or are you addressing a different regime?
My techniques, no error correction involved at all. My techniques are all about a dynamics that prepares a useful entangled state and then also amplifies the information there such that in a following readout step, you're insensitive to the extra noise that readout ends. It's not dealing with the fact that while you're inquiring the signal, there could also be things that are influencing your spins and messing things up, right? That's the thing that you would ideally love to do with error correction, right? Cancel the errors, but still have the system be sensitive to the signal of interest. And that's this linear span condition you're talking about.
Okay, thank you. Thank you very much.
Thanks.
Okay, thank you, Ash, for this very insightful talks of what you can actually do with dissipation. So let's thank Ash again, and let's move on to the next speaker.